We have seen that the imaginary number represents a rotation of 90 degrees or pi by 2 radians on the complex plane.
Yeah, but how did you get to this weird representation where j shows up on both sides of the equation?
By the end of this episode, you'll come up with it yourself.
Oh,
So let's start by deepening our understanding of the complex plane.
hmm.
Alright, we know that the real line consists of real numbers. So the complex plane consists of,
Complex numbers.
yeah, any point on this plane is a complex number. Any complex number c can be thought of as the destination from the point of origin. Note that the points on the complex plane vary in their magnitude and direction. Such entities that are defined by their magnitude and direction are called vectors. Let's project this complex number onto the x-axis to get p.
There's p on the x-axis.
Seriously? Anyway, when we project c onto the imaginary axis, we get jq. So we could reach this point from the origin by moving on the real line for p units, grow up, and q units on the imaginary line. Note that we shifted this vector from here to here with no issues. Can you guess why such a shift doesn't matter? It's because a vector is defined only by its magnitude and direction. In both these cases, the magnitude and direction remain the same. Now, how do we mathematically define this operation of stacking one vector's tail on the head of the other one? Well, it's addition, specifically vector addition. So we see that c,
That's c, and p on the x-axis. Nice choice of variables today.
anyway, we see that any complex number c can be expressed in the form p plus jq. This type of representation of a point uses the rectangular coordinate system. Considering this right angle triangle and basic trigonometry, we can compute the magnitude and the direction of the complex number c. Now let's take a closer look at this right angle triangle alone. To make things simple, let's consider the hypotenuse to be of length 1. From basic trigonometry, we know this corresponds to sine theta and this to cos theta using these ratios. Coming back to the complex plane, this vector of magnitude 1 can now be expressed as cos theta plus j sine theta. So we now have a nice connection between complex numbers and trigonometric ratios. Let's discover some more connections, shall we? But for this, we'd have to take a different perspective of things. So let's see if we could simplify this further.
What can we do?
We'll first explore another way to see sine theta and cos theta. So let's keep the hypotenuse fixed and vary this angle. This is the unit circle. Now we'll draw a graph of these lengths and see how they vary with changes in theta. Let's see if viewing sine theta and cos theta as functions could help us come up with some new representation for them. Maybe then we could come up with another way to define a complex number of unit magnitude. Alright, let's say that we want to draw this function. Now, where do we start? Cos theta exists for all values of theta, so it doesn't make sense to start drawing it from the end points. So let's start at some reference point, say theta naught equals 0.
Okay, so I'll start drawing the function from here and keep going and going and going. Oh, it looks like I'm stuck on this side forever.
That's why it's better to build the function this way. So the aim is to start at the reference point and follow the shape of the function as we draw it. The key point here is to follow the shape of the function. Now, how can we mathematically ensure that our drawing or the new representation matches the function's shape around the reference point? Well, first of all, the value of the representation should match the value of the function at this point. But the main question is, what encodes the shape information of a curve? Its derivatives. Differentiation is that operation which talks about how a function and its shape-defining attributes change over theta. So we aim to ensure that the new representation f1 has the same derivatives as the function at the reference point. Now, a choice of f1 based on polynomials is convenient as long as we appropriately scale these functions.
But why polynomials?
Such a representation is easy to differentiate, in addition to giving us a good local approximation around the reference point, captured by a0.
This still looks complicated.
Not so much at our reference point. Note that the coefficients are directly proportional to the derivatives.
And this helps preserve the shape information around the reference point?
Exactly. So this is our new representation.
What's up with the factorials?
Recall that the powers of theta are fast growing functions. We see that the factorial suitably tone these functions down. Evaluating the derivatives of cos theta at 0, we get this.
Wait a minute. All we did was to make sure that the derivatives at the single reference point are the same in both the function and its representation. How can you get the expression for the entire function for all values of theta just using information from a single point? I mean, we preserve the shape information at one point, and it somehow ensures that the shape of the entire function is preserved. That's crazy. That's officially crazy.
Yeah, I know. Isn't the idea beautiful?
Crazy. Crazy is the word.
See that adding the terms one by one builds the function from the reference point. At the limit of adding infinite number of terms, we'll converge to the cosine function everywhere. The representation of a function using an infinite series of power functions is called the Taylor series. Taking 0 as our reference point gives us a special case of the Taylor series called the Maclaurin series. Depending on the nature of the function and its derivatives, the Taylor series sometimes converges only within a small region around the reference point. For some functions, it doesn't look anything like the original one. And for some other cases, the Taylor series doesn't even exist. Anyway, other lucky functions for which the infinite series expansion converges everywhere are sine theta and the famous exponential function e power theta. It's beautiful that a higher order derivative at 0 gives the precise information about how the function changes all the way here.
Beautiful and complicated.
What do you mean?
Look, we had a single function, now we have to deal with infinite number of functions and sum them up. How is this not complicating everything?
You'll see. Let's get back to where we started. When we substitute these functions with their Maclaurin series, we get this equation, which can be rearranged like this. Do you recognize this function? How about now, after using j squared equals minus 1? This is the infinite series expansion of e power j theta.
Oh,
This function is the complex exponential. Yeah, so we have this equation before us, which says that e power j theta represents a vector of unit magnitude along the direction theta on the complex plane. This shows us that complex numbers have connections with logarithms and exponentials as well. This famous equation is named after Leonhard Euler. I really like how a shift in perspective, seeing a ratio as a function, was a crucial step in getting here. The Euler's formula, significant as it is, gains new heights when you consider theta equals pi. Ladies and gentlemen,
and others.
let me introduce you to one of the all-time favorite contestants in the beauty pageant for equations.
Seriously?
The Euler's identity, given by e power j pi plus 1 equals 0, is deemed to be one of the most beautiful equations in mathematics. It is that one equation which contains the additive and multiplicative identities 0 and 1, the irrational number pi, the imaginary number j, and of course the base of the natural logarithm e. Anyway, it's not just about how all these symbols appear in one place. It's also about how different areas like trigonometry, infinite series expansion of functions, logarithms, exponentials, and complex numbers all come together. So the Euler's identity is essentially equivalent to j squared equals minus 1, indicating that we get minus 1 when we rotate the unit vector on the real line counterclockwise by 180 degrees or pi radians. So now j, a rotation of 90 degrees or pi by 2 radians, can be expressed using a complex exponential as
E raised to j pi by 2. Ah, I see.
Yep. Okay, time for a question. Do you think this point on the complex plane could be represented by any other complex exponential?
Oh.
Have fun thinking about it.
Yeah, right.
Bye.